APP in early endosomes, which enabled an increased access to base. Therefore, more beta-amyloid is made, and this happens specifically at dendrites. So we were still not completely satisfied. We wanted to try to point out how was CD2EP controlling the trafficking of APP. So we decided to look in more detail to one single endosome. And in order to do that, we used a trick which allows us to enlarge the size of endosomes so that we can distinguish the membrane of the endosome and its lumen. And in fact, that's what you see here. So in control cells, as I told you, APP is sorted away from the membrane of the endosome, and it shows up in the lumen. So you can see the green is in the middle of the endosome, the lumen of the endosome. While when we knock down CD2EP, we see that what CD2EP is really doing is controlling the localization of APP within the endosome. You see that APP now is no longer in the lumen. It shows this donut shape just like the membrane marker. So APP is maintained on the membrane. And we can only see it because we did this imaging in the presence of an inhibitor of APP processing. Because if we don't do it, we see no APP on endosomes. Okay, and then this was using this trick that allows us to do a really strong quantification that you can see here, but we also used STORM to see at super resolution tiny endosomes like this. And this is what we could see. So in control cells, we could see APP in green in the lumen, while in CD2EP knockdown cells, it was showing up in the membranes. So what this gene, which is a risk factor for Alzheimer, is doing is actually just controlling this tiny step within one endosome of sorting APP from the membrane to the lumen. When it's not there, or maybe when it's mutated in the patients, then APP stays on the limiting membrane, and this enhances its encounter with base. And maybe also with gamma secretase, which we didn't look at, but it's also reported to be located in these same endosomes. So now what we are investigating is this increase in the accumulation of beta-amyloid sufficient to alter synapses, which are really the main target in Alzheimer's disease. And so we started to look at, in the cells, knockdown for either BIN1 or CD2EP to the number of synapses. And so far, we have some preliminary data that when we knock down BIN1, you have a decrease in the number of synapses. With CD2EP, it seems to be milder, the defect, with a decrease in the size of the spines, which are, in fact, post-synaptic, meaning that they exist in dendrites, and this is where we see CD2EP working. So what we would like to know also for the other genetic risk factors is if it's through this increase of production that synapses are affected, and we are working on this. We would also like to determine if the mutations found in the patients do cause loss of function of these proteins. Okay, so finally, I would like to acknowledge my team, and especially Florent Hubelmann, that is now back in Paris, but that was the main author on this paper, Tatiana, that worked closely with him, and now the new members that are tackling the next steps of these studies, Farzaneh, Katerina, and Cláudia. I would really like to thank the funding that has allowed me to come back to Portugal and start this line of research, and CEDOC for welcoming me at a really nice center to do research in Alzheimer's disease. Thank you all for your attention.